Welcome back. We'll see some practical two-port devices. Here first we will see Isolator. Isolator is one of the basic microwave devices on a test bench. So Isolator, what is the function is, it will send the power at only one directions. For example, imagine that one traffic police is sitting on the isolator. He will allow the signal, the wave in one directions. Okay, he won't allow in the opposite direction. So it is a function of the isolator. It will transfer the power only one direction. Where we'll use it, suppose I have a microwave source and I connected the transmission line. Is transferring all the power to the amplifier and it is connected to the antenna. Suppose the source, microwave source, maybe 4G mobile phone, it may work on 2 gigahertz, some power typically 1 milliwatts. Okay, so when power is generated, because why we need this power, because I have to send my voice and image and all the data should be modulated by using a carrier frequency. This is my carrier frequency for modulation. So I am using a source, microwave source. It is generating the power and it will be transferred to the line. It's not exactly transmission line like a coaxial cable. It will be printed in the mobile phones. All the transmission line, you can see that all are printed like a PCP lines. So that is connected to the amplifier and connected to the antennas. So here, for example, if any case, if the impedance at any point of time, if it is not matched, some arbitrary impedance, if it is not matched, here the impedance, if it is not matched, if the impedance here is not matched, then we'll start getting reflection. Okay, so once it is reflection happens, it should not affect the my source. So for that, what I will use some protection for a source, that is nothing but isolator. So this isolator will allow only the power in one direction. It will allow only one direction, not in the opposite direction. That is a function of the isolator. Okay, and how to write the S matrix? So before writing S matrix, what about the other properties of what about the S parameter properties? We'll start with the matched. So can I design the isolator with a matching in both first and second port? Yeah, obviously I should have a matching at first and second port, because if I connect this isolator to the coaxial or transmission lines, printed lines or op-amp and everything, the port should be matched. If port is not matched, it will start reflecting. I will get a reflected signal. So ideally the isolator should be matched in both ports. So S11, S22 is 0. So what about S21? S21 is nothing but what is the reflected voltage at the second port. This is always, I told, the first number is the output. The output I am getting at the second port. What is the incident of the first port? How much voltage I am giving in, how much voltage at coming at second port. That is a V2 minus divided by V1 plus. So that is S2. So this is nothing but transmission. This is transmission coefficients. How much power is transmitted. Okay. So ideally isolator should not consume any power. Whatever power is coming, it should able to transfer to the second port. So that case, whatever power you can write in terms of S matrix, means in terms of the voltage. So whatever the reflected voltage, what I am getting should be, for example, I'll write here. So whatever reflected voltage should be equals to what is the incident, how much voltage I am sending. So that incident voltage should be equals to the reflected voltage. In that case, V2 minus equal to Vn plus. So this become both numerator denominator equal to same. So S21 becomes 1. Okay, so this is S12, this S21 equals to 1. What about S12? So isolator is supposed to not allow the opposite direction. So what is S12? S12 is equals to output at first port and input at second port. So it should not allow any signal from output to the input. So V1 minus is 0. If you're giving any input here, and theoretically there should not be any output. So V1 minus is the output from the first port, that is 0, and V2 plus input to the second port, the arbitrary voltage. So this is equals to 0. So what is S matrix of isolator? S11 S22 equal to 0, S12 also 0, but S21 is 1. So coming to, okay, keep it in this only the S matrix, then we will see other properties. So what is the S matrix of isolator? Both diagonals are 0, S12 is 0, S21 only 1. So let us see whether all properties of S matrix are satisfied. One thing is, it is a matched. From the diagonal we already started with both ports are matched. So this is matched, property is satisfied. What about symmetric property? Is it S12 equal to S21? No. So there is no reciprocal. I cannot interchange the ports and work. So this symmetrical property is not satisfied. There is no non-reciprocal. Reciprocal. Okay, that is non-symmetric device. Okay, let us go to the lossy or lossless. This comes the little tricky part. So which row I should take, either first row or second row. So if unitary property should be satisfied for any port, for any row, unitary property should be satisfied if you take any row, take a magnitude square and add, and it's supposed to come to 1. Not only one row satisfying, another row is not satisfying. So if you take a first row, you take a magnitude square of 0 square and the 0 square, it is not equals to 1. So this is not a lossless device. Isolator is a lossy device. Okay, if you take a second row, 1 square plus 0 square is equals to 1. So this is second row is satisfying, first row is not satisfying. Why it is not satisfying? Since the second row, when you are giving input, it's coming as it is, the same. Okay, there is no loss, there is no power is consumed here. But in the opposite side, all the power is consumed, nothing is coming out. So one direction it is lossy, one direction is the lossless, and other direction is the lossy. So we cannot truly say it is a lossless device, it is a lossy device because it alternates the signal or consume the power. So it is in general it is a lossy device. Okay, so this is another example of two-port device is a filter, or here one of the filter is a notch filter. You know that at particular frequency only it will allow the signal. Okay, this is the resonant frequency. So this is a ring shape is there, so it's called a ring resonator because it's printed onto the substrate. So it's called a microstrip resonator, or we can say it is a patch kind of, or microstrip resonator is the right word. So we can say it's a microstrip resonator. Okay, so input is given here and output is taken from here, second port. So this is my notch. So here what is S matrix quickly? Both ports obviously should be matched because there should not be any reflection, and it should be interchangeably should be used. S12 equal to S21. Okay, so S12 equal to this S12. Whether it's lossy or lossless, that is comes with the resonant frequency. If it is resonant, working on resonant frequency, the output will be equals to the input. So that is means it is 1. Okay, or S21 is 1. So that it will be lossless only at a certain frequency. Other frequency it is a lossy. So we cannot say exactly lossy or lossless based on the resonant frequency. So quickly we will see that other two ports. These are the different filters printed on the substrate, microstrip filters. Okay, so this is a band pass filter. This input is given here. So the input is given here, output is taken here, and here input is given here. The second low pass filter, output is taken here. You can see the line where is connected to the, this is we call as SMA connector. This is connected, you used to, I think I'll write it will neatly. This is SME connector, similar like a coaxial cable. That is a BNC connector. What we use it in the function generator is the BNC connector. This is a smaller version of it, SMA connector. So here also we can connect the coaxial cable. So the input is given here in the second device and taken here, and third again same, take input here and taken here. So this is the low pass filter, this is the band pass filter and band stop. So the cutoff frequency will be designed from the design equations that will be seen in the later stages.